Jai Hind students. Today in the topic real numbers, we are going to learn about Euclid division lemma and Euclid division algorithm. And the learning outcomes are, that is what you will be able to do after learning this concept. You will be able to find the HCF, highest common factor, of two positive integers using this Euclid division algorithm. So let us explore. Dear students, do you remember the process of long division? That how can you divide a number by another number? For example, if you have to divide 14 by 4, how will you do it? Yes, it's very easy. Here 14 is dividend, 4 is divisor, 3 is quotient and 2 is remainder. Here is a challenge for you. Here the dividend is missing. We do not know what the dividend is, but we know that what is the divisor, we know the quotient and we know the remainder. Can you find the dividend? I hope you all can find it very easily. It's so easy. Let us take another example. If you want to divide, say 23 by 4, then how can you do it? Simple. Now, the dividend 23 can be expressed as 4 into 5 plus remainder 3. Now in general, if in place of 23 and 4 we have any two positive integers, say a and b, on dividing a by b, if we obtain the quotient q and remainder r, then how can we express the dividend a as dividend a is equal to the divisor b into the quotient q plus remainder r. It is a well-known result. So this simple result can be stated as, if we have two positive integers a and b, and on dividing a by b, if we obtain quotient q and the remainder r, then we can write the dividend a is equal to the divisor b into the quotient q plus the remainder r. This is very simple and familiar result, and you have been using this since your elementary classes, that is from class 3rd or 4th, when you learned the long division process. So there is nothing new in this result, but from now onwards we will call it by a new name, that is Euclid division lemma. Now let us see what happens with the remainder. For example, when we divide consecutive numbers 16, 17, 18, so on respectively by 4, can you tell me what remainders do we obtain? On dividing 16 by 4, we obtain the remainder 0. On dividing 17 by 4, we obtain remainder 1. On dividing 18 by 4, we obtain remainder 2. Then on dividing 19 by 4, we obtain the remainder 3. But on dividing 20 by 4, the remainder becomes 0, and thereafter the remainder repeats itself. Can you observe what is the minimum and maximum value of the remainder r here in this division? Yes, minimum value of r is 0 and maximum value of remainder r is 3, that is 1 less than the divisor 4. So what we conclude here? We concluded here that when we divide any number by 4, then the remainder can take values at least 0, or it can be greater than 0, but it is always less than the divisor, that is 4 here. Similarly, when we divide numbers 14, 15, 16, 17, so on by 7, what can you say about the remainder? The minimum value of the remainder is 0, and it can take values 1, 2, 3, 4, 4, 5 and 6 but not 7. Therefore, value of r can be 0 or greater than 0 but is always less than 7. Therefore, in general, the value of the remainder r can be 0 or greater than 0 but always less than the divisor b. Can we have any other remainder for a particular division? No. Therefore, the remainder r in a particular division is unique. Now let us generalize our result and state the famous Euclid division lemma. If we have two positive integers a and b and we divide a by b and we get two unique integers q and r as quotient and remainder, then we can write the dividend a is equal to divisor b into quotient q plus the remainder r. And what is the condition on r? That r can be 0 or greater than 0 but is always less than the divisor b. That is, the value of r lies between 0 and b but always less than b. As you have been using this result since your elementary classes without knowing its name, this result was perhaps known for a long time, but it was first recorded in the written form by the famous mathematician Euclid of Alexandria in his famous book Elements. This book has 13 parts and he mentioned this result in part 7 of this book Elements. In mathematics, as you all know, every statement or result has to be proved. That is, it requires a proof. A lemma is an already proven statement which is used to prove other statements. Although this result is quite easy to understand and easy to state, it has many applications related to the divisibility properties of integers. And the Euclid division algorithm is based on this lemma. And what is an algorithm? An algorithm is a series of well-defined steps which gives a procedure for solving a particular type of problem. Euclid division algorithm is a technique to compute the highest common factor, that is HCF, of two given positive integers.
This technique of calculating HCF of two numbers is very helpful to us in solving many daily life problems, and also it helps you in competitive exams where you may have to find HCF of two or more integers quickly. So let us learn this technique.
To find HCF of two positive integers, say 455 and 42, we divide the greater number by the smaller number and we obtain the quotient and remainder. And how can we express the dividend? As we have done earlier, 455 is equal to 42 into 10 plus 35. Here the remainder is 35, that is, remainder is not equal to 0. So we carry on applying Euclid division lemma on the remainder and the divisor of the previous step. This method works because the HCF of 42 and 455 will be equal to the HCF of the divisor, that is 42, and the remainder, that is 35. Now we can express 42 using Euclid division lemma, and here again the remainder is 7, that is not equal to 0. So we will continue to apply the Euclid division lemma on the divisor and the remainder of the previous step, that is 35 and 7.
On dividing 35 by 7, 35 can be expressed as 7 into 5 plus remainder 0. Here remainder is 0. Therefore, the divisor in the last step, that is 7, is the HCF here. So we write HCF of 455 and 42 is 7.
Let us recapitulate the Euclid division lemma with the help of following flowchart, which can be treated as a mind map. The first step to obtain the HCF of two positive integers a and b is that we apply the Euclid division lemma on a and b. That is, we divide the greater number by the smaller to obtain the quotient say q and the remainder r. And we see that if the remainder is 0 or not. If the remainder is 0, then the divisor in the previous step, that is b, will be the HCF of a and b. And if the remainder is not 0, what we will do? We will repeat the step 1. That is, we will apply again the Euclid division lemma on the remainder and the divisor of the previous step. And we will continue this process until we get the remainder 0. And in the last step, when we get remainder 0, the divisor of that step will be the HCF of the original numbers a and b. So I hope you must have understand this concept of Euclid division lemma and Euclid division algorithm.
Now let us try to solve some problems based on Euclid division algorithm. First problem is, show that any positive odd integer is of the form 6q plus 1, 6q plus 3 or 6q plus 5 where q is some positive integer. इस प्रॉब्लम को सॉल्व करने से पहले आइए यूक्लिड डिवीजन लेमा को रिकॉल करें. If we have two positive integer a and b and we divide a by b, then a can be expressed as b into quotient q plus remainder r. Let us start by taking a as a positive integer. Let us apply this Euclid division lemma by taking b equal to 6. That is, when we divide a by 6, then if we get q as quotient and r as remainder, we may write a is equal to 6q plus r. What can be the value of r? R can be, remainder can be 0, 1, 2, 3, 4 or 5. Putting the values of r here, a can be of the form 6q plus 0 means 6q, 6q plus 1, 6q plus 2, 6q plus 3, 6q plus 4 or 6q plus 5. Now recall from the question that a is a odd integer. Which of them do you think are odd integers? 6q is obviously an even integer because it is a multiple of 6, therefore it is divisible by 2. 6q plus 2 is also even because it is a multiple of 2. Similarly, 6q plus 4 is also divisible by 2. Therefore, we are left with only 3 options, that is 6q plus 1, 6q plus 3 and 6q plus 5. Therefore, any positive odd integer can be of the form 6q plus 1, 6q or 6q plus 3 or 6q plus 5. Show that square of any positive integer is either of the form 3m or 3m plus 1 where m is some integer. Now again start with the Euclid division lemma, which states that for any two positive integers a and b, there exist unique integers q and r such that a can be expressed as b into q plus r. Let us take b is equal to 3, that is, divide a by 3. A can be written as 3q plus r, and what can be the values of r? 0, 1 and 2. Putting the values of r here, we get 3 values of a, that is 3q or 3q plus 1 or 3q plus 2. Let us find the square of this integer a. First case, a is equal to 3q, then squaring both sides, a square is equal to 3q whole square, 9q square, which can be written as a multiple of 3 as 3 into 3q square. Now what can you say about this factor 3q square? We know q is integer, so q square is also an integer and 3q square is also an integer. Let us consider this 3q square as any other integer, say m. Therefore, we have expressed square of the integer a as 3m. The second case is equal to 3q plus 1. Squaring both sides, we get a square is equal to 3q plus 1 whole square. Then by expanding it using the identity a plus b whole square, we get 3q whole square plus 2 into 3q into 1 plus 1 whole square, that is equal to 9q square plus 6q plus 1. And again in first two terms 3 is common, then we can write it as 3 into what is left here, 3q square plus 2q, and what is left in the next term, 1. Now observe this factor in the bracket. What can you say about this? Q is integer, therefore 2q is also integer, 3q square is also integer, and sum of two integers is also an integer. Therefore this factor is integer. Therefore let us replace this integer by another number, say m. So it can be written as 3m plus 1. Let us discuss the last case, that is a is equal to 3q plus 2. Squaring both sides, expanding, we get 9q square plus 12q plus 4. We can write it as 9q square plus 12q, and this last term 4 as equal 3 plus 1. By doing this, we see here that 3 is common in these first three terms. Taking 3 as common in first three terms, we get 3q square plus 4q plus 1 and plus 1 in the last term as it is. Now this factor in the bracket is a integer, as we discussed in the previous case, so we can replace it by any other integer, say m. Therefore it becomes 3m plus 1. So we conclude that square of any positive integer is either of the form 3m or 3m plus 1, where m is any integer. Dear students, in this video we discussed about Euclid division lemma, Euclid division algorithm, and some divisibility properties of integers using Euclid division lemma. So do revise this topic at your home and complete the following assignment. Thank you very much.